Today's paper is about an algorithm that is unusually efficient at a relatively obscure task. The authors have found a way to surface uncovered petri-net transitions in cubic polynomial time. So what is a petri-net exactly? It's a mathematical model of a distributed system, but it's commonly represented visually as a diagram. You'll generally see three types of shapes. Circles, these are places. They represent states, conditions, or resources in the system. Rectangles, these are transitions. These represent events or actions that change the state. And arrows, these are arcs. They indicate the flow or relationship between places and transitions, showing how states and actions are connected. Let's take a deeper look at the rectangles, the transitions, the actions. At any given time, a transition can generally be either enabled, that's ready to fire, disabled, not ready to fire, or fired, that's executed. But a transition can also be uncovered. This means that the transition is not part of any T invariant. In other words, it's not included in any cyclic behavior or functional loop within the system. If you can find uncovered transitions, they are likely the lowest hanging fruit that you can fix in order to begin optimizing the system as a whole. Accordingly, there is a whole body of research that concerns finding and surfacing uncovered transitions. It's not that they're hard to recognize when you see them, it's that in a sufficiently large and complex system, they're hard to locate. If you try to brute force it and have your algorithm exhaustively explore the entire state space of the petri-net, it's going to take too long. Luckily, there are a number of more modern approaches to this that you can use to save time. The most common is probably the Martinez-Silva algorithm. So that brings us finally to today's paper. These authors have produced another algorithm, and this one completes in polynomial time, specifically cubic polynomial time. If you're already subscribed to our email newsletter, you'll be getting this episode in text and audio form delivered to your inbox in the next few hours. Journal Club. The latest academic research explained in plain English.